more practice with that. So what we've seen so far is that we did these limits of the sums, and we had those f of x sub i's and the change in x, the areas of the rectangles that we added up. And we saw that come up when we did area. Okay, we've also could use that if we're trying to find distance traveled by an object, or there's a lot of other situations. But one thing that we haven't ever seen, in all of these situations, weren't we just adding up areas that were positive? Everything was always above the x-axis, but is every curve above the x-axis? No. So we have to have that option where things can go below the axis. A shorthand for this, okay, the limit of the sum of all this stuff, that gets cumbersome to write. There is a shorthand that's called an integral. All right, so an integral is like a skinny tall s. All right, it goes from A to B. That's like a starting and a stopping point. So if I'm adding up the area from, let's say, 0 to 3 under the curve x squared, we could say the integral, it starts at 0, it ends at 3. My function is x squared. And then there's this dx at the end. The dx is attached to the integral. Those two things go together. You can't have one without the other. All right, so anytime you have an integral, you have that dx at the end. It's basically telling us what our variable is. So that dx is telling us x is a variable that's changing. Okay, so if we had an expression with multiple variables, everything else would be treated as a constant. X would be the only variable. So integral and that dx have to go together. So in this notation, f of x, the thing we are integrating, is called the integrand. That's like the curve we're finding the area under. A and b are called the limits of integration. A is the lower limit, the starting point, and B is the upper limit, or the ending point. So it's just a shorter way of writing this thing that we were already calculating in the last section. So this slide is just saying what I already told you, that dx goes with the integral. It's telling us what our variable is. So we can use these integrals to find area under a curve. Okay, and we know if we want to be more accurate, we have to have smaller rectangles. And if we want the perfect answer, the real answer, what has to happen to our number of rectangles? Right. More rectangles, right? More and more rectangles. So the number of rectangles has to be going to infinity to get the true area under the curve. Okay? And so that's what the integral does. It is when we have an infinite number of rectangles. So it does give us the exact area under the curve. But we have to take into consideration when things dip below, this area is like area between the curve and the x-axis. Anything above the x-axis is positive. Anything below is negative. We call that the net area, like the positive area minus the negative area. So we will be focusing on that probably more next week. We'll get into dealing with the positive and the negative area. The integral is going to take care of everything for us. We don't really have to separate them out. It's only when we have like an absolute value function or something different that we're going to have to adjust. So we are going to be able to integrate any continuous function. So just like all the derivatives and stuff, it had to be a continuous function, same thing for integrals. We have to have continuous functions or a set number of breaks in the graph so we can break it up and do areas of pieces. All right, So notation-wise, this should look familiar. Dx in the integral is like this change in x that we were seeing before. Remember, the change in x is your ending minus your beginning divided by the number of rectangles. The x in our function is that x sub I that we were doing before. Remember, x sub I is how we are counting our x's. So it's our starting point plus multiples of the change in x. So what we're going to work on today is using those two notations. So if I want to calculate this integral using what we have already done, we have to be able to calculate, just like we did before, the change in x and the x sub I to start. So my change in x is where you end, which is the top, minus where you begin, which is the bottom, divided by the number of rectangles, which we want the true answer, so an infinite number of rectangles. So we're just going to keep it as n. So my change in x is 4 over n. X sub I is our starting point. Where did we start? 0. And think about this. We're starting at 0. And to get to the next one, we have to add our change in x. So this would be 4 over n, right? The next one would be 8 over n, and then 12 over n, and so forth. So it's the change in x times I. How many multiples of 4 over n have we added together? So this just turns into 4 over n I. So if we are doing this based on what we already know, that means we are doing the limit when the number of rectangles goes to infinity of the sum from 1 to n, f of x sub I times the change in x. Okay, that's what that last slide told us. That's what we're doing. What do I mean when I say f of x sub I?
We put x sub I back into our equation.
That is going in for these x's. So we have 4 over n I cubed minus 2 times 4 over n I. So we replace every x with x sub I, 4 over n I. And then we have this change in x, and change in x is 4. So that's like the area of the rectangle, length times width. The length, the height of them, is what you get when you plug your x into your function. The width is the same every time. That was the 4 over n. Okay, does this seem familiar? Like the last question on the quiz or the homework assignment before that? So if we start simplifying this, if I cube 64 over n cubed I cubed minus 8 over n I, and that whole thing's times 4 over n. So if we distribute 64 times 4, what's that give us? 256? Over n to the 4 I cubed minus 32 over n squared I. Have I lost anybody? What do we do next?
We have to separate the two.
Mm-hmm. And we can do the sum of each of them. So at the point when you use your I cubed and I formulas, that's when the sum goes away. So right now, I'm doing my sum formulas. So that means the summation symbol drops. Coefficients just stay. The I cubed formula is n squared n plus 1 squared over 4. Times 32 over n squared times my I formula, n times n plus 1 over 2. So we're using these formulas so the sum drops and we get these expressions for the i's. It's not pretty, but it's just algebra at this point, right? So we're going to simplify everything we can. If you want, you could drop 2 of these n's out. 256 divided by 4 would just be 64. Drop one of those n's. Plus a 16. Square that. We really want to break these into individual terms. So if I start splitting this up, I distribute, I get 64 n squared over n squared, so 64. Plus 128n over n squared, so 128 over n. Plus 64 over n squared. This one you're distributing a negative 16. So minus 16n over n, 16 minus 16 over n. Have I lost anyone? Now we do the limit. So if n goes to infinity, that's 64. Anything with an n on the bottom turns into 0. So 64 minus 16, notice how we just naturally subtracted off what's below the x-axis. It happens for us. And we get 48. So the total area contained under this curve is 48. And that's what the positive and negative just automatically subtracting off. All right. A lot of calculation. The calc part of it is at the beginning. Can you take this integral and turn it into this limit of the sum? From there, it's just a lot of multiplying and simplifying things. All right. Let's go to this one. Sorry, I did leave you blank slides, but I guess I forgot to tell you there was a blank slide following that one. I was trying to be kind, but it only works if I tell you it's there. This one's not asking me to calculate it, it's just asking me to write the integral. So can we take the limit of the sum and turn it back into the integral? So the integral, this skinny s, where would it start? And it ends at 2. Right? That symbol right there takes care of the limit and the sum. Now we have this expression. That stays, except you don't use x sub i's. Or, this had an x sub I minus 1. Sometimes you might have an m for what stands for midpoint. I'll explain that in a little bit. It doesn't matter what this is. That's my variable piece. So when I go back to my integral, I'm just changing it into an x. So no matter what the variable is, don't worry about it. It just goes back to an x. The final thing change in x, what am I missing from this? Change in x becomes your dx. And that's it. Okay, so the limit of the sum, that's the integral piece. This function, we just put it back into an x. Change in x becomes our dx. And that's my integral. It's like the first 5 questions on your homework. Just writing these integrals. I'm not asking you to calculate, just can we go back and forth between the notations. Let's try another one where we have to calculate them. So this one I went back to the integral. So we need to change it into the sum because we know how to evaluate these sums. So first we need change in x. How do I get the change in my x?
Difference in start.
Yep. So it's just the top minus the bottom. So 5 minus 2 over n. So we get 3 over n. All right, then we need x sub I. How do we get x sub I? Perfect. What is my starting point on this one? 2 plus my change in x, so 3 over n times I. All right, a little bit uglier. It's nicer when we start at 0, but we can still do it. What do I change this integral to? Infinity of the sum from 1 to n. Okay, my function. We are taking that, but what do I replace my x with? So the x gets my x sub I, so that's the 2 plus 3 over n I squared. And then what do we change d of x to? The d of x is my change in x. Did everyone follow how all the pieces go into the puzzle? So now it's algebra. I can't do the sum until I clean this up a little bit. If I square that, I have to write it twice in FOIL, so I get 4 plus 12 over n I. 9 over n squared I squared. And this, show as much or as little work as you need. Okay, I'm trying to show enough that you guys can follow, but if you're combining steps in your head, that's okay. Just don't mess up. We distribute our 3.
How'd yesterday go?
Okay. Can I combine like terms and distribute my 3 over n? So 12 plus 4 is 16 times 3 over n. Give me a 48 over n plus 8 over n squared I. So 81 over n cubed I.
I know you got all sometimes, so it's not all that. I'll be out there. Too, bro.
All right, so that was just a bunch of multiplying. Now what?
So for each one.
We separate each one and do the sum. So when we do the sum formulas, we drop that sum symbol. All right, 48 over n. That doesn't have an I in it. What happens when you add that up over and over and over again? Yeah, because you have to take it times n, the number of times you add it up, right? It's just a constant. So if I'm adding that up n times, it gets multiplied by n. 108 over n squared times the I formula is n times n plus 1 over 2. Big 1 over n cubed I squared formula is n plus 1 times 2n plus 1 over 6. So now we're back to simplifying all this mess. So 48 over n times n is 48. You can reduce some things if it helps you. All right. So we get 48. 54n over n is 54. It's 54 over n. Plus, if I take my 27 times 2n squared, so 54n squared over 2n squared, and 27. Plus 81n over 2n squared, so 81 over 2n. Plus 27 over 2n squared. Now it's finally set up where we can do our limit, so anything with n on the bottom turns into 0, so we get 48 plus 54 plus 27. And 29. I know that's a lot. Do we have questions on any of that? What is on my floor? I keep crunching on something. So no questions at all right there? I'm just that good at explaining everything. Problem like this, and there's just no room for a question because I explained it that well.
Must be the case, Miss.
Must be. It's the only possible answer. All right, you guys do the next example. So integral, what number goes on the bottom?
0.
And on the top? Okay. What do I do about this?
So except your x is not just
X cubed plus x sine of x. And change of x becomes? And that's right. All right, I'm stopping here for today. We will do some more of those nasty integrals on Monday. So I'm giving you a handout. This handout is due Tuesday. So we won't be done with this section at that point, but we'll have gotten through the first half of it. So let me give you this and talk about what you could do at this point.
Okay.
So 1 through 5, you should definitely be able to do, and if you spend like more than 5 minutes on that section, you should ask me a question. Okay, those are like the last example we just did. All you are doing there is writing the integral. So it shouldn't require a ton of time or thought. 6 through 9, I would like for you to skip for now. We'll talk about those on Monday. 10 through 14 are those long intervals. If you need more space, you're welcome to do them on another sheet of paper. Obviously, I don't expect you to do all of these by Monday. We will be practicing more of them, but you should try to get a couple of them at least. Especially the first 2 won't be too nasty because there's only one term, so those should be much nicer to calculate than some of the ones we've done. So you guys have time right now to start. Like I said, it's not due until Tuesday.